through a little video tracking experiment that I did with a falling ball. So I used the stock video from Vernier Video Physics, and this is what I came up with. I've got a position versus time graph here on the top with a quadratic fit, and a velocity versus time graph on the bottom with a linear fit, the slope of which is negative 9.84 meters per second squared. So the purpose of today's class is to sort of get you to think about how what we did with all the graphing can be related to the algebraic equations that you use in problem solving. So first I want to remind you that the area here, the integral between this curve and the axis, represents the displacement, okay? And this is on the velocity time graph, the area represents displacement. And we're going to relate that to the displacement on the position time. So I'm just going to draw my velocity time graph right side up so that we can have a more sensible look at it. So I have this statement here that the area is displacement. So the area of that triangle is 1/2 the base times the height. Well, the base is time, but the height is velocity. But I want to point out something kind of neat, which is to say that the velocity is actually increasing because of the acceleration. Now, what I mean by that is that if you have an acceleration of 9.8 meters per second of free fall, what that means is that the velocity goes up by this amount for every second. So we're going like at 1 second, 9.8, 2 seconds, 19.6, 3 seconds, 29.4, and so on and so on. So you can say in general that at any time t, the velocity is acceleration times time, and if you plug that in to your area calculation as the height of your triangle, you get this kind of neat equation, 1/2 at squared, where a is the acceleration due to gravity of 9.8 meters per second, and t is the elapsed time. So the last step for us is to make an algebraic statement. You can see on the top, I've got the displacement is 1/2 at squared, and on the bottom, I've got v equals at. Now, for free fall, for objects falling in Earth's gravity, we're going to give the acceleration a special letter. We're going to call it g, okay? Now, instead of saying 1/2 at squared, you can see that I've got 1/2 gt squared, where g is the acceleration due to gravity, or 9.8 meters per second. So this formula applies to all accelerations, but when we're talking about free fall, we use g. So for my last slide, I want to introduce you to the 5-step process for problem solving. Step 1 is to read and reread the problem. Step 2, make a chart of everything you know and then the thing that you want to solve for. That making a chart is really critical. Step 3, find an equation in your toolbox. Step 4, plug in the numbers and solve. And step 5, check your units and check for reasonableness of your answer. So the question here is the following. You drop a rock off a bridge and you time its fall at 2.5 seconds. How far was the drop and how fast was it going upon impact? So first step is to read and then reread. You drop a rock off a bridge and you time its fall at 2.5 seconds. How far was the drop and how fast was it going just before impact? So we're going to take the how far question first, and we're going to make our chart of what we know and what we want. So if I drop a rock, the acceleration is free fall. So I'm going to write that down. If I time it, clearly I know the time. How far is the displacement, or change in x, or change in y, I guess we could write that. And that's all we have. So that's step 2. We've made a chart of what we know and what we want. So if we look in our toolbox, we can see that there is an equation ready-made for this problem. And sure enough, it's this one. Delta x equals 1/2 gt squared. So I'm going to take my equation, I'm going to plug in the numbers, and I'm going to solve. This is now step 4. 1/2 times 9.8 meters per second squared times 2.5 seconds. The whole quantity gets squared. You can use 10 for the acceleration due to gravity if you want to approximate, but this is how you plug in the numbers. So I'm just going to bring up my calculator really quick. So I've got my 1/2 times my 9.8 times 2.5 squared, and that gives me, let's see, 30.6 meters. But I want to make sure that those units worked out. So I would say it's meters divided by seconds squared times seconds squared, because that squared goes through the units as well. So I get 30.6 meters, and I'm going to check this now for reasonableness. Now, that is a pretty tall bridge. 30 meters is, roughly, I would say, 100 or so feet. So, that bridge is pretty far up there. Okay, now, how fast was the object going upon impact? We would make a new chart. What do we know? What do we want? We know acceleration is g. We know t is 2.5. We now know the displacement, and we want to find the velocity. And I look in my toolbox, and I have, oh, hey, look at that, a formula that says v is equal to g times t. So I'm going to plug in my numbers. 9.8 times 2.5 seconds gives me roughly 25 meters per second. Okay, the per second cancels with the seconds, and my units work. I get roughly 25 meters per second. Okay. So to summarize, when you've got a physics problem, you want to read and reread. You want to make a chart of what you know and what you want. You want to find an equation. You want to plug in and solve. And then you want to check for reasonableness. And then finally, you want to submit your work with pride. So if we've got a ball falling, we would be able to calculate how tall the building was just by timing it.